Okay, so welcome again. We now begin lecture 20. So we are midway of the course now. So in this lecture, we'll again delve on the composition, weight fraction calculation, etc. So first, let me just recap the last lecture. So in the last lecture, we talked about the tri-line rule, which allows us to determine the compositions of two phases in equilibrium in the two-phase region in a binary phase diagram. So what you do is that you basically draw, so if you know the overall oil composition and if you know the temperature, then at a fixed temperature you draw a horizontal line. This horizontal line intersects the two-phase boundaries on either side. So if you are in two-phase region, let's say liquid plus solid, then intersection of this horizontal line with the liquidus will give you the composition of liquid phase, and intersection of this line with the solidus will give you the composition of solid phase in equilibrium with the liquid. So you will have two phases in equilibrium whose composition can be known. Then we looked at lever rule. Lever rule is basically a rule to calculate the weight fraction of two phases in equilibrium with each other. So once you know the two-phase composition of two phases, you can also calculate the weight fraction of two phases in equilibrium with each other. So in this lecture, what we will do is that we will derive the lever rule. How does the lever rule come about? So let us say we have a two-phase equilibrium. So this is C naught, this is let us say C alpha, and this is C beta. Okay, two phases in equilibrium, and this is the tie line basically. Okay. Right. Now at a fixed temperature, of course, T1. So temperature, let us say, is T1, that is fixed. Overall composition C naught. Okay. Now it is a two-phase equilibrium, which means you have alpha plus beta region. Alpha phase of composition C alpha and beta phase of composition C beta. So let us say for this overall composition, and the weight fraction of alpha is F alpha and the weight fraction of beta is F beta, such that F alpha plus F beta is equal to 1, okay, because the mass is conserved. Now amount of solute in any phase is also conserved. So since amount of elements is also conserved, which means let us say amount of, so total amount of element is also conserved, amount of B in alloy, let us say, is equal to amount of B in alpha plus amount of B in beta. So if amount of B in alloy is given as C naught, C naught was the overall composition, which is nothing but when you are going from A to B, it's percentage amount of B. So amount of B in alloy is C naught. So amount of B in alpha will be equal to fraction of alpha phase multiplied by the composition of alpha phase in percentage B, let us say that is C alpha, and then we have fraction of beta phase into composition of beta phase, that is in C beta. We know that F alpha is equal to 1 minus F beta. Okay. So this is the second equation. Okay. The first equation was this equation, and the second equation is this equation. From the first equation, can write this as a result. So, you can write C naught is equal to 1 minus F beta into C alpha plus F beta into C beta. If you work it out, so you have to rearrange it in such a fashion so that you can determine FB. So, F beta can be found as, from this expression, F beta will be equal to, so if you just have to rearrange this so that you have a common factor F beta. So, it will become F beta into C alpha minus C beta, which is equal to C alpha minus C naught, or C naught minus C alpha. So, F beta will turn out to be C naught minus C alpha divided by C beta minus C alpha. So, percentage of beta will be equal to C naught minus C alpha divided by C beta minus C alpha into 100. Similarly, you can work out F alpha, which is equal to C beta minus C naught divided by C beta minus C alpha, which is equal to basically 1 minus F beta. So, this is how you derive the lever rule, which is essentially based on the principle of mass conservation. So, basically the mass of in a two phase mixture, the weight fraction for a given composition is equal to they add up to 1. So, for 100 gram you will, so consider you have 100 grams. So, 100 gram will have certain amount of alpha and certain amount of beta. So, you can calculate the weight fractions, though those weight fractions must add up to 1. Similarly, the amount of solute is also conserved. So, whatever the phase fraction may be, the total amount of B that is present in both the phases must be equal to what is present in the alloy. So, that is how you determine the phase fraction. So, this is what these are the few things that are important about the phase diagrams to quantify various things. So, you can determine composition of the alloy. If you know the composition of the alloy and temperature, you can determine composition of phases and you can determine their phase fractions. Let us first look at the examples of common eutectic phase diagrams and common phase diagrams that are present in alloy systems. So, basically isomorphous systems, you have copper nickel alloys, then you have silver gold, you have germanium silicon, and then you can have a pseudo binary system such as Al2O3 Cr2O3, where this is one component, this is another component. So, all of these make nice isomorphous perfectly soluble systems. If you look at the eutectic systems, in the eutectic, your first very common alloy is the aluminum silicon alloy. Then you also have lead tin alloy, which is used as a solder. Part of iron carbon phase diagram shows this kind of eutectic reaction. In the pseudo binary system, you can have MgO, Al2O3 system, and so on and so forth. So, these are eutectic alloys. And then third one, let us say peritectic systems. In case of peritectic, the melting point difference is quite high. So, part of iron carbon system, high temperature part, high temperature low carbon part. In case of this is high temperature high carbon part. So, high temperature low carbon part shows peritectic reaction. Similarly, copper zinc system, that is brass, copper tin system, bronze. So, there is a substantial difference between the melting point of two elements, that is why they show peritectic reactions. You can have nickel, rhenium system, and various other systems where you have large differences in the melting point, they show peritectic reactions. Often in many alloys, the phase diagram is not only eutectic or peritectic or Isomorphous, it's a mixture of few reactions. So you can, part of the phase diagram could be, so you can have several reactions taking place in single phase diagram. So for example, you can have a phase diagram like this. So your iron carbon phase diagram, as I drew earlier also, is so you have peritectic reaction on this side, and then you have this eutectic reaction, then you have eutectoid reaction, so this is what you will have in iron carbon diagram. You will have liquid phase, so you will have gamma, alpha, liquid plus Fe3C, liquid plus gamma, gamma plus Fe3C. This will be liquid plus alpha, alpha plus gamma. This is alpha plus, so this is no, sorry, this is not alpha, this is delta, and this is alpha, this is alpha plus Fe3C. So you can see that this is eutectic, this is peritectic, and this is eutectoid. So this is iron carbon system. You have several other systems which are very complicated. For instance, you can have copper zinc system. In copper zinc system, I will come to them later on, but in copper zinc system you have first peritectic reaction here, the second peritectic reaction here. So it goes through a series of peritectic reactions. Okay. So, and then and so on and so forth. So this is temperature, this is Cu, this is percentage zinc. So you have alpha, liquid plus alpha, you have alpha plus beta, you have beta phase, then you have liquid plus beta, then you have beta plus gamma, then you have gamma region, and it just keeps moving forward. So you have a lot of these peritectic reactions one after another. So this is CuZn system. So this is how you can have multiple phase diagrams. Now what we want to first do is that we have to first understand how different phases develop in a phase diagram, then how can we calculate their fractions in a given phase diagram. So now first let's do an analysis of copper zinc system, let's say, sorry, copper nickel system. So you have Cu, you have Ni, this is temperature, this is Xni, okay, we know this is liquid, this is solid, and in between we have liquid plus solid. So let us say we have alloy of composition C0, okay. So what happens at this point? Let's say we start from this temperature T1. So at T1 we have 100% liquid of composition C0. So what is it going to look like? It's going to look like something like this. If you look at it in a, so if you look at it under a microscope, for instance, you will have 100% liquid. Nothing else. You come to this point now, cross the liquidus boundary. So at T2, when you come to T2, you start forming little bit of solid. So solid starts to form, so which means some solid, and the composition on amount of that solid can be given by lever rule. So you can apply tie line rule and lever rule to calculate the composition. So tie line will give you composition of alpha and liquid, and lever rule will give you amounts. So let us say let's zoom this portion at T2. So at T2 we are something like this. Okay. So this is at T2. Our overall composition is this. This is C naught. This is solidus. So this is CS, and this is CL. So since the solid has just begun to form, the difference between CL and C naught is very, very small. So percentage. So as a result, percentage solid, which is equal to C naught minus CL divided by CS minus CL. Since this is very small, it is extremely small. So you have mostly liquid with some particles of solid forming. So what you have here is at T2, you have mostly liquid phase with tiny particles of solid forming somewhere. So this is solid. So this is solid and this is liquid, and solid of composition CS and liquid of composition CL, but very little in amount, just a few specks, just a few pieces here and there. Now as you go further, so basically percentage solid you can work out as C naught minus CL divided by C alpha minus CL into 100, and this will be very minute. So let us say for an example, if C naught was if C naught was 70 and if CL was 69 and C alpha happens to be, let us say, 85 minus 69, then you can see that this is 1 divided by 16 into 100. So it's a very little amount. It's only 5-6% or so, 6 something percent. And if it's, let's say, 69.5, it's even lower. So it would be 0.5 divided by 16. So you see, it would be 1 divided by 32 basically. Okay. So which is a very small amount of solid. Now let us do one thing. Let's go to point 3, T3. At point T3, so when we go to point T3, you can draw another tie line. So this is, let's say, 70%. At point T3, you have formed more solid, and solid composition is given by, so you have formed more solid. So this is solid composition which has moved along this line, and this is the liquid composition which has moved along. So you can see that as you have formed more solid, the liquid has become depleted in solute, and solid also has become depleted in solute as compared to the solid which had formed earlier, but the solid composition overall is higher than the overall composition of the alloy. So, at T3, if this is the zoomed up view, so this is at T3 and this is C naught, this is C alpha, this is CL. So, this was 70. Let us say this works out to be, first we took 85. Let's say this turns out to be 80. Okay, if this is 80 and this turns out to be, you see, was saying it was 6. So, it's, let's say, I don't know, 60. Okay. So, if this is 60, 70, 80, then percentage alpha in this case is 70 minus 60 divided by percentage solid, as alpha is same as solid. So, pardon me for swapping alpha with solid. So, this is 10 divided by 20 into 100, so it's 50%, and as a result percentage liquid is also 50%. So, how does it look like in the microstructure? So, you have liquid, and these solid particles which are present earlier, they have now grown bigger. So, now these solid particles have grown So, this is solid. So, solid of composition C alpha, liquid of composition Cl, which is about 80 and 60, and now solid is about 50% F alpha and Fl is about 50% also. So, solid has grown in mass. The moment you reach T4, T4 is a temperature which is here just above the solidus. So, when you are at T4, then liquid composition is this, solid composition almost same as the alloy composition, you have very little liquid left. So, what you have here is at T4 is situation like this. So, most of it is solid. The solid will impinge into each other. So, it is mostly solid. With a few pockets of liquid left here and there. So, you might have some liquid here, you might have some liquid here, and mostly it is solid. So, these are called as grains of solid. So, this is solid grains, alpha grains of composition nearly C naught, and you have some liquid C liquid of composition Cl. So, if you look at the phase boundary now, this is your liquid solidus, this is your liquidus, you are here T4. So, this is your overall composition C naught, this is your C alpha and this is your Cl. So, your C percentage liquid will be tiny, because C alpha minus C naught divided by C alpha minus Cl, this is very tiny. So, what you are left with is basically nearly 100% solid with very tiny amount of liquid present. Solid composition is nearly same as the alloy composition, and liquid is highly depleted in solute with composition Cl. And the moment you cross over below T4, you will have 100% so you will have 100% solid of composition C naught. So basically what you have done is you have started from this point T1 where you had 100% liquid, gone through formation of solid in sequential fashion with decrease in the amount of liquid slowly and gradually until you cross point T4, below which it's 100% solid. So this is how the microstructure develops and the phase fractions change. We will do further analysis based on these in different systems and take it further. Thank you very much.